Before I introduce myself, before I talk about, of course, the topic here, I have a few questions for you. First question, who knows what a graph database is? Okay. Have you ever used a graph database? Okay, 2. Okay, great. So, okay, then the third question is, have you ever used Neo4j? Wow, 0. Okay, perfect. That's great. The reason I'm asking these questions is because I submitted 2 talks. One was the introduction to graph databases, and the other was the next bit, which is artificial intelligence and machine learning with graph databases. And so I thought, okay, what should I do? Because if the audience doesn't know about graph databases, there's no point to jump to machine learning without at least a little bit of context on this, right? So no worries, I got both covered, but I will try to balance these aspects by giving you a little bit of information on graph databases, and then of course talk about artificial intelligence, machine learning, and why it's so important. First of all, very quickly, who am I? The classic who am I in graph mode. My name is Ivan Zorati, I'm the speaker here. I work for a company called Neo4j, which if you wonder about the name, Neo is like Neo in Matrix, 4J, because we started as Java libraries a long time ago, so the J stands for Java. I'm presenting a talk, which is, well, the one you know, and of course you also have ideas about the date and time. These are properties within this graph. This is already a graph, but we'll talk about that in a few minutes. I'm a product manager for Neo4j, the database specifically. The company has other products. I'm focused on the database itself. If you have ever heard about Neo4j as a company, which is not unusual, we are what we define ourselves as a graph company. We pretty much are the leaders in the graph database market. We are more than 250 employees today. The headquarters are in Silicon Valley, but we also have offices mainly for all the software development and engineering in Sweden. I come from the good old days of MySQL. It's a deja vu because it was exactly the same, like starting in Sweden and then moving to California. That's similar. Lots of funding because building databases is crazily expensive and hard. And we have a quite interesting list of customers and partners. But this is everything I have to say about non-technical stuff, all right? The database, I can tell you, is we have the typical dual approach, the community and the enterprise edition. I'm going to tell you what is not community, so you are 100% sure of what is something you can try and use it as much as you want, and something that actually you may need to pay for it, or just use it as a trial first, of course. The first question that we always ask when we have presentations or introductory presentation is, what is a graph? What do you think a graph is? And sometimes people say, oh, this is a graph. Okay, we don't do this. We don't do these kind of graphs. We do this kind of graphs, which are more mathematical graphs, right? Where we have edges and vertices that are connected together, and these connections will make a big difference. So we, in database terms, call the vertices nodes, and the edges are called relationships. And these objects have properties. That's another super important point that in other databases and other structures we do not see, because mathematically don't have this idea of the properties. And we also identify these objects with some labels, which is a way to identify that we have nodes of a certain type with that label, or relationship of a certain type with that other label. So If you, again, still remember the very first one with the speaker and the talk, the labels were speaker, talk, the properties were my name, the name of the title of the talk, etc., etc. The relationship was, of course, the connection, and there was a type of relationship which is similar to the label, which was this present, very, very similar to a concept of a verb that you use. We are quite ambitious and pretty proud of what we do, because we think that we can help in changing the world. That's kind of crazy, you may think, but actually, by the way, you are free to take all the photos you want, but the slides will be all available publicly, so don't worry about this too much. I mean, you can do it, of course. I mean, I'm not stopping you, just saying, if you don't want to spend a lot of time taking pictures, they will be all available through, of course, DataOps and also on LinkedIn. I would say we are proud to say we can change the world, because, okay, I'm going to say this now immediately, and then you'll see what I mean. I come from the relational database world I worked in relational databases for probably 25 years or so. This is something new, something different. It does not replace relational databases. It's very, very complementary. And combining these two things together, I think, makes a huge difference. So if you ever heard about Panama Papers, you know, the whole idea of what happened in Panama with all these interesting bank accounts that were investigated by journalists. Well, all the Panama Papers was discovered thanks to Neo4j. We connected the bank accounts with the people and all the connections among different people, and the journalists used Neo4j to check what was going on and see where one bank account was leading to, and identify all the direct connections, etc. And then there are some other examples that are maybe less well known, like NASA providing information around what they give as a learning for readers on the website, and they use Neo4j to identify what is more interesting for a specific reader, somebody who comes to the website and is interested in checking, for example, some historical flights or information about planets, galaxies, etc. And for eBay, that's another example. There are many, of course. How to help in what we call the conversational commerce, how you can go from one step to another and provide the best possible information through this user experience. And it is all related to a very, very basic concept that in the modern world, everything is connected. And if you know relational databases very well, you know that the most difficult thing to do is to connect data. You have tables and you start joining them, and one join is good, two joins okay, three joins, four, forget it, and so on. And when you have hundreds of joins, that's not going to work. That is a problem. And that's where I think graph databases, not just Neo4j, comes and play very, very well in this role. So, we have the idea of a graph. I mentioned the fact that there are properties connected to this graph, and we create what we call a property graph model. What does it mean? It means that our nodes that are objects in this graph can be labeled. So for example, I have 3 nodes, 2 persons and 1 car here, and they have labels. So there are 3 nodes, they're all the same, but they have a different label, and this is very, very important. Just to give you an idea, in Neo4j, a label is an index, because yes, we don't need indexes, but they help. And so we label and index nodes. And then we connect them through relationships. And by type, which is another index, again, another label, we can identify also the direction of this relationship. So as you can see, we have a bidirectional love, hopefully, otherwise we may have some problems between 2 persons. And we can say that one person lives with another person, and that might see, it might have a meaning, like the owner of a house is maybe this person compared to this other. And both drive a car, and it might be the same car. Of course, I'm just giving you a very, very simple example. There may be much, much more complicated structures. If we add the concept of properties, we define the fact that the persons have names, they are born at a certain date, and they have a Twitter account. Some have a Twitter account, others do not have a Twitter account. So again, if you know very well relational databases, of course you know that you have a table and you must have those columns, and if you don't have data in a particular column, then you have a null value. In this case, you don't have the property. So if this person doesn't have a Twitter account, there is no such property like a Twitter account. We have properties also on relationships, and of course on another node here, like for example, if we're talking about car, we may say, oh, I got a Mini Cooper, and that is of course other two properties. Why are graph databases so cool? And this is not just Neo4j, it's any graph database. So you can see others, of course, available in the market that you may want to try or use. There are lots of use cases, and you will soon find out that the use cases here are different from the use cases from the relational databases. So fraud detection is one of the most interesting and most important ones. The anti-money laundering, all the e-commerce fraud, credit bank accounts fraud, they are immediately a perfect fit for graph databases. Think about the model, and if you follow the links, well, not now of course, but you will follow the links, you will see some examples where you have a graph model where you identify a credit card with accounts, and how easily you can spot, well, relatively easily you can spot that maybe a credit card is somewhat associated to more than one person, which is weird, or the fact that connections are strangely gone to different regions in a similar or close time that shouldn't happen. So that means that there must be a fraud or a warning at least. So if you wonder how your credit card sends you a warning because something is going wrong, well, actually they're using maybe graph database, maybe not, but the similar concept. Another example is what is called defined as master data management. So in today's organizations, you have lots and lots of data, like documents, links, your user accounts on different type of sites or services inside your organization. You may have a 360 degrees view of your internal employees, of your customers, etc., etc. And all these connections fit extremely well in a graph database. In this case, maybe it can be hierarchical, but if you look at it from a different angle, it's still a graph. Or you can have, and that's another interesting one, a recommendation engine. Think about the typical Amazon people who bought this, also bought this other thing. Okay, the silly or simple way to use it is, well, I can check the basket of one customer who actually had this item, and I can also recommend this other item. Or you can analyze not just the basket, but you can analyze the behavior of this person, of this account. And that is where recommendation becomes really, really interesting, because you go and predict and you identify the social structure, you identify the interests of your users. Knowledge graph, if you want, is somewhat, in my opinion, similar in terms of concept to the idea of the master data management. And again, when you have lots of data, documents, information, etc., that you may want to analyze. And here we enter into also definition of, for example, natural language processing that can fit very, very well again with graph databases, so you can start analyzing even documents, emails, stuff that comes and goes through users. You can imagine now that there are things that can be extremely helpful and good. There may be also other things that if they are in the hands of other people who are maybe a little bit less, let's say, nice and kind, they may also do some harm. But that's the technology and what you can do with it. So for example, you can also control monitoring for systems, data infrastructure, network infrastructures. Again, a network, at the end of the day, you can represent it as a graph. And then social media, absolutely, why not? I mean, when you start connecting people through LinkedIn, Twitter, Facebook, you have a graph or a social graph. And if you are familiar with everything that happened, I mean, I live in England, I'm Italian, living in England, so as an immigrant, I kind of see what happens with Brexit and all this stuff, and what happened behind the scenes by identifying some people, some accounts, and addressing those specific accounts in a way to move the behavior of other people around it. It's not science fiction, it's something that you can do with graph databases. And so, at the end of this long list, you have artificial intelligence and machine learning in general. Graph databases are identified as a perfect match, the storage structure behind machine learning and behind artificial intelligence, because at the end of the day, you take a graph, you have the data structured exactly as it's needed for these algorithms to run. But Neo4j, more specifically, is a database. So we represent graph, but the concept is that we take this graph in a mathematical model and we store it. So it's a database that can help you in storing and retrieving data. And if you are familiar with other databases, I hope, and of course, we are not much different because we rely on transactions, we have ACID, we rely on isolations levels, we have the idea of work with the scalability, availability that is a common issue for all the other databases. We have the very same problems and we try to address them in pretty much the same approach. Sometimes it's not that easy, like for example, people keep asking us, what about sharding? And how can you split a graph? How easy it is to split a graph? If it's a small graph, then maybe. If it's a complex graph, like, I don't know, kind of a Facebook or LinkedIn example, good luck. So it's not that easy. And even more, we are a graph database where we define ourselves as a native graph. Somebody more technical may say there is no such thing. At the end of the day, we talk about bits and bytes and we have pages, and that's exactly what we have, but we try to map as much as possible a graph model into the storage structure. Another important point is that we have a specific language which is designed for graph. It's called Cypher. And it is something that hopefully, if you will try it, if you want to give it a go and spend some time with it, if you know SQL, from SQL to Cypher, it will be pretty simple. And then you can use it with graph, but with your ideas you already have in mind about SQL. I have some examples. What's the secret sauce behind this? How can this be so cool, so good? But more important, answer questions of hundreds of thousands of connections much, much faster than a relational database. And I'm talking about literally from seconds or milliseconds compared to minutes or hours. The secret sauce is that the connections are what we define as first-class citizens. It means that a connection is not a link that is identified through indexes, etc. It is a pointer from one element to another, and it may be even in the same page. So when you retrieve a page with a node in it, you may already have the other node that is connected together. And that makes a huge difference. Then, of course, sometimes we also need indexes, as I mentioned before, because we refer to different labels, etc. That helps, but it's a kind of a second stage. So, in terms of read time, we have the retrieval time much faster. In terms of writing, we immediately write also the connections. We don't need to duplicate or address even extra indexes, so more writes. You see that we reduce the number of writes we execute. So that's, if you are a little bit more familiar with what are the internals or the basics of how you can read or write data in relational databases, okay, this is what you do instead with graphs. You start from stores here are, put it simply, files, and you have like blocks, and they are like fixed size, so you can immediately go and point to one of these specific elements, which are the nodes, and you have some properties already predefined there, or you can just overflow on more dynamic elements if you have, like, for example, big strings, etc. I jump on a node, and I can immediately identify within another store, which is maybe already cached, the relationships all connected, and the properties that are all connected together. So this, if you just follow it a little bit, I'm going quite fast now because we have only 45 minutes, but you see that there are way less operations compared to what you need to do with a large number, of course, of elements and indexes in a relational example. Everything I described so far is available everywhere, especially in community. We are a typical open core structure. Clustering is enterprise only. So if somebody wants to use community only, I'm sorry, there is no causal cluster. This is what we know. It's not casual, it's causal, which is slightly different, of course. The swap of this, the XP, as you would say with the Vim, makes a big difference between you and S. And it's the fact that we have a consistent cluster based on what we call core servers internally that are based on a Raft consensus algorithm. The Raft consensus algorithm, which is something, if you are familiar with Paxos, similar, but with the idea of this consistency over time, gives you a guarantee that your node within a cluster may be behind, but is timely consistent. So if you identify an instant which is T0 on a machine and another T0 on another machine, you have exactly the same structure on these two nodes, for example. But of course, this node may be behind, like there is maybe a replication lag. That's possible. If you are MySQL guys, the concept is, we are not talking about synchronicity, but the concept is similar to the log and the relay log that will be applied eventually. I said before, we have, of course, the concept of a schema, and if we want, we can enforce schema, we have some constraints, etc., but we are also schema-free. So you can start, and you may say, you know what, this node has some properties, this node, same type, but doesn't have these properties. I'm allowed to do that, so I can use it as I wish.
Is there an advantage to using one rather than the other? Because obviously schema sounds great and things, but I guess schema-based means it's more efficient, or...
And the answer is absolutely yes. I mean, when you start, you say, oh, okay, I like this idea of saving some space. And then when you start having like a few billions nodes, things are slightly different. So yes.
You have the choice.
Yeah. I mentioned the query language. Cypher is the query language. I don't remember in English the term, but you see here we define the node, and then this is the relationship, which is somewhat similar as description, even if it's in characters connected to another node. So here we define the create command, which is the same of insert in SQL if you want. There is a label. We may not have labels, but it's a good idea to create nodes with a label. We define within brackets the properties of this node. We may or may not have a relationship, and this is the type of the relationship and the direction. And then we have another node, and the same point, label and properties, if you want to record them one. So that's a creation. and this is a select, a match. Match is like select. So this means I want to find the person with name done. This is equivalent of where. We have where as well, but you may do it as you wish. You may do it here or in a where clause. Who loves whom? And we don't know who. So we are looking for this person. And then we have a return, which is the equivalent of the select part, which returns who, which is this person here. So we know that we have one person, and we want to see who this person loves. And we have problems if we have more than one here. That's a different story. Come on. We have a database, we have graphs, we must have something a little bit nicer to show, not just numbers and characters. So the browser is what you see here. Actually, I had it somewhere, but we don't have much time, so let me go very quickly. When you install and run Neo4j, you go to 7474 by default, the port, or 7473 HTTPS, and you can basically write cipher over there, and you can see the output in graph mode, or you can jump on a tabular mode, or JSON structure, etc., etc. As a simple thing to do, it helps a lot, and it's really, really cool. When you start having like billions of nodes, of course, this is different. We also have a desktop, and everything I said here, apart from clustering, again, community, you have it too. Desktop is the desktop environment where you may connect multiple graphs or databases here, and you may have like extra projects with other applications that are combined all together. So with this, you can use JavaScript, for example, and create your own application. It's relatively simple, and it is also very, very helpful for many. Like, for example, we have customers and users creating their monitoring tools, or their simple graphs, automatic graphs application to create new nodes or modify them. And then we have an analytical tool for power users called Bloom. Bloom is something that in natural language or near natural language, with the help, of course, of indexing, full text indexing, helps us in creating things like this. And this is the non-community side, meaning that Bloom is an enterprise solution. But you can simply say, for example, I want to see, I don't know, my patients, and I want to identify the patients by a specific element, which is maybe the area where it runs, and by point and clicking or writing in natural words over there, you can basically start analyzing this stuff. If you know tools like Tableau and Click, we used to say this is kind of a Tableau for graphs. Okay. If you like all of these, and you say, oh, by the way, I don't have time to install it, or I don't have space on my laptop, just go and choose one of the sandboxes. They are available for you, you connect, and because you have a browser, you can simply go through via HTTP, HTTPS, and use one of them. There are some already available for you with graphs inside. So you may have, for example, examples of a crime investigation, of how to do network and monitoring. There are like, well, the Women's World Cup, guess what? Of course, it's something quite good for today, and things like Trump World or whatever you may want to try and like. Now, if everything that I described so far makes sense, well, if we have like something that we already know, and we have identified what to put into our graph, good. Let's carry on with this. We can use a cipher language, and it's great. If we have our graph, and we don't know what's inside, we have no idea how to extract data, then we need something a little bit more powerful and sophisticated. And here comes the the concept of graph algorithms libraries. So Neo4j is based on lots of interesting plugins. One of them is an algo library, we call it, which is a set of algorithms that use normally data scientists and users in playing with data and find much more sophisticated information. For example, we may have like some real examples. This is pretty much, of course, the topic for this talk. In terms of data propagation and pathways. So see how the data propagates and the nodes modify themselves, and the attitudes of these nodes in a graph modify themselves following a certain pattern, or something related to the flow of data within a graph, or what is the interaction of nodes within these particular graphs. These are some examples, and again, you follow the links. There is much more documentation, normally university studies or research, etc. So this is an example in 2010, so a little bit old, but still absolutely valid, where there was a research around the propagation of delays on US flights. So you can basically start from east to west, and you realize that for whatever reason, delays usually start from the east. Guess what? It might have something to do with time zones and how the flights actually start from this. And then you can see, for example, that the ones in green are okay, the ones in purple are actually delays, and the size and the definition of the large delays is related to the size of these elements, of course, which is just a graphical representation. But what you see here is that when you have like your graph stored, you can run algorithms that can identify where these delays have been spreaded and also what are the starting points. Another example, typical example of how these algorithms can work might be something like this. This is something that Massimo and I used to, in the old days of MySQL cluster, used to find quite interesting. The routing engines, or the raters were called, when with the advent of IP telephony and the idea of VoIP, we were basically checking what was the lower cost compared to quality in terms of I want to call from Spain to Thailand, for example, and I want to identify the lower possible cost but keeping the quality up to a certain level. You need, or let's say by doing it in real time with a graph algorithm, you can really run it with this algorithm and a simple Cypher query. Or another example, which is even more interesting, which is the fact that there is interaction between groups, is something like this. So this is a graph, and of course, it doesn't give you much, but just to give you an idea, behind the scenes, the red and green are this is Belgian Telecom. The green or the red, one of them is French speaking and the other is Dutch speaking, and you identify the communication and phone calls. Guess what? They are pretty much all within the same language, with a little bit of interesting interaction in between. So that is something that helps in predictive analysis and identification on how to improve the telecommunication network and where to identify the telecom pipes that you may want to build for your infrastructure. That's another example. Overall, we have something like in the order of about 40 different algorithms. There is a book that is for free. You can download it, a PDF. Well, not the book in paper, that costs, and don't do it because, of course, we want to save trees and paper, but it's available in PDF, and you have like examples on how these algorithms work. And you have like algorithms related to graph centrality, community detection, similarities, etc., etc. So this is really, really interesting. I have a few examples here that might be helpful for you, or you might be interested, like pathfinding. Pathfinding is probably the simplest one, and that was the first thing I did when I joined Neo4j. I loaded all the data from flights in the US, and I started trying to find what was the shortest and left path from one airport to the other. I mean, sometimes it's helpful, at least if you travel a lot. But that's just a silly example. But the idea is that you can find, with the algorithm, what is the shortest path. And again, in a small graph like this, it's easy. You can immediately see it. But when you have billions of nodes, maybe things are a little bit more complicated. Or you may identify all paths and then find a weighted way to organize or sort them. So there are, for example, algorithms. This is something you can find on GitHub, where you have the shortest path, the Dijkstra or A star. There are different algorithms to find what is the path, like in San Francisco, New York, from going from A to B, with different structures. In the demo on GitHub, you will see also the queries, the cipher queries that can be executed. So I leave it to you, of course, in order to do that, if you are interested. That's quite cool, by the way, I think. And then there are other algorithms, like the centrality algorithms are related to PageRank, which is, of course, something that is really, really so nice and dear to Google and all the page ranking we may want to identify. So which node within a graph is the most important? And this is like socially extremely important for social networks, but also for fraud detection and crime prevention, but also for healthcare. I mean, to identify diseases and see how they can be stopped from spreading, and elements like this. Or maybe from the spreading, the betweenness. Which node has the most control over flow between nodes or groups? So again, and the healthcare is one of the main areas where graph databases are used. Like the German Diabetes Center is all using, well, there are researchers using Neo4j to fight diabetes, for example. Another algorithm is the degree, the number of connections that every node has. So we identify how many connections a node may have, and then we can also interact with these nodes. And the closeness, which node is closer to a certain group or a specific group of other nodes. And regarding the page ranking, there are some very interesting examples on how PageRank can be used not just for page search and identify the list in Google, but also to, for example, to fight diseases or identify near extinction animals, etc., etc. Page ranking, talking about machine learning, is super important because you can basically retrofit. You can load the data that you identify as ranking and reuse it and reiterate all these results. Some examples on similarity. When we talk about similarity, we identify nodes that are similar. The idea of the recommendation engine that I described before, that is somewhat related to this. In a way, you may say, okay, I have a user who is interested in such items, for example, on Amazon, and okay, you may be interested too, but not because you put this item in a basket, but because your activities tell me that you may be similar to this other person, which I, of course, for privacy, I'm not showing you, but I can give you more recommendations. Or there are like elements like what you socially prefer, and then again, there may be analysis that might be helpful also in terms of how I can, as a researcher, identify some simple things like movies or interest, etc., or maybe more interesting in like medicine, etc., etc. Algorithms on community detection refer to the fact that you don't have only similarities on nodes, but similarities on groups of nodes and their relationships. So you may have, again, here for medicine is really, really important because you may have like elements on how drugs to drugs are related and they may affect each other. These are examples. Or there is an interesting research on what is called the Twitter polarity classification, which identifies the concept of who to follow in Twitter and what is more prominent in terms of person who can push more or let's say influence more other users on Twitter too. And this is quite fascinating how many things you can see on this. I'm almost done. I think I have still 5 minutes, right, Nasser? Okay.
Right.
Oh, this is even more interesting because this is the link prediction is something that goes. Thank you. That goes to the point where I'm going to predict what will be the next connection among nodes. So I'm saying I'm starting with a specific element, and the prediction of these algorithms gives you a possibility to identify that the next connection will be between these nodes. And that is again something that will help you in identifying how, for example, socially, people move towards an area or another, especially for social networks or for other researches. So, what does it mean? It means that we have like possibilities that are really unthinkable until like only a few years ago, of things that we can do with databases that you cannot do with relational databases, as I said before. That's why I think they are so exciting. And if you can combine them together, you get, of course, the best of both worlds. And this is not just for terrorist networks or social elements, etc., but also in terms of art and music and elements that are more literally fun and also important for us as human beings. You can really work around what can be better for the society in terms of for example, investing more in some particular architectural structures or musicality, etc. I would leave it like this. And I already talked about this example, which is similar to the concept of the link prediction, the idea of the common neighbors, where you identify what is defined as potential triangles and closing triangle by identifying the current status and what might be the next. So, just to summarize, more resources available. I already mentioned the fact that we have a book. There is a sandbox with the graph algos already in there, so you don't need to download it. If you want to play with it, just connect and click, and it will be on for a few days. I don't remember the time, but anyway, there is a time bomb that, of course, after a while it says, okay, you can download it and save it on your laptop. And you also have training. So if you want to know more, there is a training available. You can go, register, and do the online training, which hopefully will be really helpful for you, and you will enjoy it. And if you have questions, I think I have a few minutes left. Yeah?
Does Neo4j allows to for any kind of meta model where you can add semantics to the properties? For instance, saying that live with is symmetric.
Sorry, say it again with an example?
Yes, the property lives with is symmetric, so it can be read from the two sides like the ontologies.
Yeah, you can do that. Yes, especially with within the relationships, for example. That's another possibility.
How do you scale?
How do I scale? Well, not me. How does Neo4j scale? In different ways. So the concept of a clustering you saw before. Okay, we have the idea of the core, and in that case you have a concept of a leader and follower, which is similar to the master-slave if you want. And then we have what we call read replicas. And read replicas have just as different protocol, what we call catch-up protocol, which is again similar to asynchronous replication if you want. That's for reading. For writing, well, we are quite memory intensive, as you can imagine, although, of course, it's all a matter of caching. So we have GPUs and memory intensive machines that use, and we are working on finding the magic solution of distributing graphs on multiple machines, which is something that will come with the next version.
Even what sort of data set sizes typically are you seeing, and what's large, what's medium, what's ranges?
great question. So the large never goes beyond a few terabytes at the moment. It's not uncommon to have like AWS machines now that use 1 terabyte of RAM and they use Neo4j with that, which is of course quite expensive, but you can see also the advantage of using it. The idea of having the magic view of sharding here is the fact that you can actually reduce much more the size. And one of the first steps is it will be out next month. We split the database and we can have like multiple devices, block devices working on that, and that will be already some sort of extra scaling. But yes, I mean, usually it's less than 10 terabytes per machine.
The comment that you're saying is that memory as a caching thing is something that's very important for the way the
yeah, because we are really talking about use cases where real time of billions of rows is important, which is kind of, completely different story.
Is there a minimum amount of memory to run your business on a laptop?
You can run it on really like a half gigabyte or so. It's absolutely fine. We are talking about really working with terabytes of data, like a booking.com like thing. That's a different story. Okay. I think, the time is over. So thank you.